So welcome to the wonderful world of buffers, and this is when the fun part of AP Chemistry starts. And it's going to take a lot of thinking and visualizing, especially as you go into the titration part. And this draws a lot on the acids and bases section as well as equilibrium. So the first question here is, what is a buffer? And simply put, it is something that resists changes in pH when you add hydrogen or hydroxide ion. So what is a buffer made of? It is a weak conjugate acid-base pair. Or you can say weak base and it's conjugate acid as well. Okay, let's take, for example, HNO2. Okay, and when you look at the weak acid, HNO2, when it undergoes hydrolysis with water, okay, we'll go ahead and write the equation out here. The equation for the hydrolysis. And remember to write this as an equilibrium because this is a weak acid. And so a buffer composed of this is going to have loss and loss of HNO2 and NO2 negative. Okay, now keep in mind that a solution of pure HNO2 is going to have loss and loss and loss of HNO2 and only a teeny tiny bit of NO2 negative and H3O positive. Okay, so that's assuming it's a non-buffered solution. Okay, but if it is buffered, you're going to have loss and loss and loss of the HNO2 and loss of the NO2 minus. Okay, and I'll draw you a picture shortly too, so you can envision what it looked like at the molecular level. But the primary way that you know you have a buffer is if you have appreciable amounts of a conjugate acid base and its base. Okay, and they both have to be weak. Okay, so it's very important that you understand that strong acid have negligible conjugate bases, so that would not make a good buffer. Okay, so how does the buffer exactly resist pH changes when you add OH minus? So let's visualize what the buffer composed of H3PO4, which is a weak acid, and H2PO4 negative is conjugate base. Okay, now the solution I've drawn for you right here is actually just mostly H3PO4, okay, and it's undergone hydrolysis, and because it's a weak acid, it has only ionized slightly. Okay, notice that you have these two, the hydrogen ion and the H2PO4 minus ion. Okay, so this is non-buffered. Okay, then to make it a buffer, you could add a source of H2PO4 negative, and you can do that by adding, a salt of it, an ionic compound like NaH2PO4, which is highly soluble, so that when it goes into the water, the Na plus ions and H2PO4 minus ions will dissolve, and you'll end up having more of the conjugate base. Okay, and so that is how you would make it a buffer solution, because you have loss and loss and loss of the H3PO4 and loss of the H2PO4 minus. Okay. So what's going to happen here is if you add OH minus, okay, think about what it's going to react with. Okay, this is the base, and bases react with acid. So the acid in this particular equilibrium is the H3PO4 right here, and that's what the OH minus is going to react with. So you're going to end up having an equation like this: OH minus plus H3PO4 is unidirectional. It essentially goes to completion. Okay, and it's going to gain the E hydrogen, OH minus will gain the hydrogen, and then it's going to make more of the H2PO4 minus. Okay, and that is the net ionic equation that shows you exactly how the buffer works. Okay, now if I did, like, say, a BR and AR table, and you can see exactly what's happening. Let's say that you had like 1 mole of this and 1 mole of H2PO4, and you only add a slight amount of OH minus. such as 0.005. We're going to ignore the water. So in the end, you're going to have 0 moles of the OH minus and 0.995 moles of the H3PO4 and 1.005 moles of the H2PO4 minus. And the ratio between the H3PO4 and the H2PO4 minus 1:1 is very, very stable at 1.005 and 0.995. Stay the same, more or less. It's very close to a 1:1 ratio. So the buffer, you can see here, is resisting any major changes in the pH. Okay, technically the pH will change, but not very much. Okay. Now, if you were to add an acid to the buffer, the acid is going to react with the base, which in this case would be the H2PO4 minus. And you definitely need to make sure you know how to write an adionic equation for what happened when that undergoes, when that reaction happens. Okay? So how does the buffer resist pH changes when OH minus is added? Remember that bases react with acid, and acid will react with bases. So the next thing you might be wondering is when you might see or use buffers. And let's talk about situation 1, which is real life. Buffers are very, very important for helping maintain pH in biological system. If you think about it, we do need some, acid in our body. We need hydrochloric acid, for example, because that helps with digestion. But at the same time, hydrochloric acid is so strong, it's got a very, very low pH and high concentration, and we don't want to let that spill over to the rest of our body. So our body, our blood especially, is composed of buffers to help maintain that pH. Okay, and another example of when you might see a buffer is a swimming pool. You want to keep the pH, relatively in a narrow range so that it's not too caustic or corrosive to your skin. But at the same time, you want to put in chemicals like bleach that have very high pH but help to keep the pool clean. So the buffers help to maintain the pH of the swimming pool, or as I've seen some of the discussions on the discussion board, like hot tub. So you use buffers to help maintain a stable pH so that when acids and bases are added, the pH won't change very much. Okay. You're going to learn about this a little bit more, but in a titration between a weak acid and a strong base, or a titration between a weak base with a strong acid. So let me give you an example of one. Let's say you have HNO2, once again, undergoing a titration reaction with OH minus. Okay, this is unidirectional, and so this becomes NO2 negative plus H2O. Okay, and if you start off once more in the beginning, let's say you start off with 1 mole, and you add a titration of 0.1 mole of OH minus, and let's say at the beginning of a titration. Okay, then, when the OH minus is limiting, you'll have 0.9 moles of the HNO2, 0 moles of the OH minus, and 0.1 mole of the NO2 minus at the end. And I'm going to ignore the water. Okay. So in the end, you have here some of the weak acid and some of the conjugate base. So you have a buffer present in the beaker at this point. Okay, now keep in mind that that doesn't apply if, for example, you are at the equivalent point. Okay, let's say you have 1 mole of this, and you add OH minus, 1 mole of that, and then you get to the equivalent point. You have 0 moles of this, 0 moles of that, and 1 mole of the NO2 minus. Since you only have NO2 minus present, only conjugate base present, that is not a buffer. Okay, so buffer only exists at a certain point along the titration. It cannot happen between a buffer of a strong acid and a strong base because the conjugate base is negligible in that case. So you got to be really careful about when you see a buffer during titration. So that's going to come up very soon. Okay, and so once again, this is very, very important. A buffer contains both an acidic species to neutralize the OH minus and a basic species to neutralize H plus. And they both have to be weak. Okay, and let's make sure you understand why a strong acid, strong acid and a conjugate base will not work. Okay, we'll do HCl. Okay, and when that undergoes hydrolysis with water, it only goes in one direction. And then you have Cl minus plus H3O positive. Okay, so a strong acid is going to have loss and loss almost exclusively Cl minus and H3O plus, and a very teeny tiny bit of HCl. And so this would not make a very good buffer because if you were to add, say, strong acids such as nitric acid, HNO3, okay, the H plus ion are not going to take out the Cl minus because Cl minus is negligible conjugate base, so it's going to be quite unwilling to accept the hydrogen from the HNO3. And therefore, by adding a strong acid to this system here, you're just going to make the system even more acidic, lowering the pH as a result. Okay, if you would add OH minus, that would neutralize the H3O plus, but the solution would still already be, very, very, very acidic, and just maybe a little less so by adding the OH minus. But again, you're going to see that when you're doing the titration curve. Okay, but you definitely need to make sure that you remember to focus on the weak conjugate acid-base pair. Okay. One very, very useful calculation to help you out would be called the Henderson-Hasselbalch equation. And let's take a look at how that equation is derived. Okay, I'm going to have you take a look at this expression, and we have to make use of your skills from when you did logarithm in pre-calculus. So we know that Ka equals x negative H3O positive over Hx under the hydrolysis equation. If you we take the log of both sides, so that gives you log Ka equals log of the x minus H3O positive over Hx. And we can expand your logarithms on the right side by making this log x negative over Hx plus log H3O plus. And then I can rearrange the equation by moving the log H3O plus to the left side. So I'm going to, don't want to run out of room here, negative log H3O plus, and I'm going to move the log Ka to the left side, to the right side, and say negative log Ka plus log of the x negative Hx. And negative log H3O plus is the same thing as pH, and negative log Ka is the same thing as pKa plus log x negative over Hx. And that is the same as this equation right here. You do not need to memorize this equation as this is provided to you on the AP Chemistry formula sheet, but it is incredibly useful. You can use this equation as long as you have a weak acid conjugate base pair, weak base conjugate acid pair. Okay, you have to have appreciable amounts of both of them. Okay, you couldn't use this in the last chapter, the last unit when we were finding the pH of a weak acid, because you didn't have much of a conjugate base present. Okay, but in a buffer, you have both of those present, so you can use this. Okay, you can also use moles, okay, or molarity, but the thing about molarity is that you have to use it as long as the volume is the same for both the X negative and the HX. Okay, and that's going to come up a few times on the pretest and maybe the homework as well. But moles will work under Henderson-Hasselbalch, but molarity, it can be used under certain circumstances, so make sure you remember that. Okay, you can use this again anytime you have appreciable amounts of a weak conjugate acid base pair. Okay, and this kind of goes along with what I was saying earlier. When you have a small amount of OH minus added, the OH minus react with HX to produce some more of the conjugate base and water. Okay, and because the ratio remains relatively constant, the pH is not changing. That's why we're so focused on the ratio from the Henderson-Hasselbalch equation. Okay, when you add H plus, some of the X minus is consumed, you'll have a decrease in X minus and an increase in HX. Okay, and let's look at it in terms of the Henderson-Hasselbalch equation. Okay, that pH, and the ratio is flipped over here, but that doesn't really matter. Okay, plus log X negative over HX. Okay, so if you were to add the acid, H plus in this case, that's going to reduce the X negative a little bit, and the HX will be increased. So this value will be, as a result, a little smaller, but it will not have much of a big impact on the pKa. So as long as this ratio doesn't change by a whole lot, okay, the pH will not change by a whole lot either. Okay, and you'll see some examples of that in the calculation soon. Okay, let's talk about buffer capacity. What buffer capacity is the amount of acid or base that can be neutralized before there's a significant change in the pH. Okay, if you look at these two buffers, okay, this one has, let's see, 8 of the HA, and this one has 8 of the A negative. So that's the buffer, assuming that HA is weak. This one is 4 of the HA and 4 of the A negative. Okay, and they both have the same pH because the ratio between these is 1 to 1. Okay, however, the beaker on the left side, this buffer, has a greater buffer capacity, meaning I can add much more of a strong acid or a strong base to this than I could to this one without causing a change in the pH. So the higher the concentration of the weak acid base pair, the greater the buffer capacity. Okay, it would be like having, if you were trying to defend a fortress, it would be like if you had more soldiers over at the fortress, you could, hold out against the enemy longer than if you only had a few soldiers. Okay, and this is just stressing this again, that a buffer contains a weak acid and conjugate base pair, but also a weak base and a conjugate acid. So a weak base, for example, such as NH3, and its conjugate acid being NH4 positive. Okay. Take a look here. Let's take a look at this sample problem right here. So take a moment to read it, and then we'll dive into it. Okay, so let's first actually focus on this part of the question about the H plus is 2.7 times 10 to the negative 2 if it is only 0.1 molar HF. So this case, the pH would equal the negative log of that number, 2.7 times 10 to the negative 2. So that would give you a pH of 1.57. Okay, so now let's take a look at it if you had both HF and NaF in it. Okay, so the first thing I'm going to do is to write down the hydrolysis equation for HF. Okay, when you add it to water. Okay, and that gives you F negative and H3O positive. Okay, and then we're going to do this the ice table way first. Okay, you have 1 molar of this and 1 molar of this. Okay, and 0 of this. Okay, then Okay, and we're going to find out the pH of this. So this is going to dissociate a little bit. So this is going to be minus x, plus x, and plus x. So that gives you 1 minus x, which we're going to assume to be negligible. This is going to be 1 plus x, and we're also going to assume that to be negligible, just say 1. And then this is going to be x. Okay, so then we do the Ka, 7.2 times 10 to the negative 4 equals x. Okay, when you plug it into the expression. Okay, then we take the negative log of that number. Okay, so let's do negative log of 7.2 times 10 to the negative 4, and that gives you 3.14. Okay. And then the ionization of this, we'll take the 7.2 times 10 to the negative 4 divided by 1, not really necessary, times 100. Okay, and then I'm just gonna be safe, so I don't trust my mental math this time. That's gonna be 0.072% ionization. Okay, which shows that we can definitely ignore the X. Okay, and think about how the addition of the conjugate base affected the solution's acidity. Okay, if you think about it, Le Chatelier's principle, by adding F negative, by adding more of this, then more reactants were produced, so more of the HF, and some of the H3O plus was consumed. And since the H3O plus decreases, that causes the pH to increase. And also the addition of the F negative caused the Q to increase. So because the equilibrium shifted to the reactants, there was less ionization, and that's why the percent ionization decreased as a result. Okay, so that's a way to think about it on a scale in terms of the big picture, but these are the calculations that demonstrated why that happened. Okay, now I can also show you the shortcut I have to find the pH of the buffer, and that is using Henderson-Hasselbalch equation. Okay, once again, I'm going to write that equation out for you. pH equals pKa plus log of the F negative, the conjugate base, over the acid. So we can take the negative log of the Ka value, 7.2 times 10 to the negative 4, plus log F negative over HF, happens to just be really 1 over 1. And hopefully you, pre-calc teacher, make sure you guys understood that log of 1 is 0. So the pH just equals the pKa at this point, which is going to be very important to know for your titration, by the way, but you should learn about that soon enough. And that would give you a pH of 3.14. So you can see how Henderson-Hasselbalch can be very useful, but remember, you're only limited to doing it when you have both the acid and a conjugate base present. Okay, and they both have to be weak. Okay, so this wasn't in your lecture notes, but I do think it's important for you to see the impact of a buffer when you add it to when you add a strong acid or a strong base to it, and see how the buffer can really help out with that. So earlier we established that the pH of this system is 3.14, and let's assume that we have 1 liter of the buffer. So we have 1 liter. Okay, which means that you have, as a result, 1 mole of HF and 1 mole of F minus, since the molarities are the same. Okay, and then let's say that we add 0.1 mole of, let's say we start off with sodium hydroxide, so OH minus. So the OH minus is going to react with the HF in one direction to become F negative plus H2O. So before the reaction and after the reaction, you have 1 mole of this. Okay, we have 0.1 mole of this and 1 mole of that. We can ignore the water. Okay, after the reaction, this will be down to 0.9, 0, and 1.1. And remember what I said that you can use moles in Henderson-Hasselbalch. So pH equals pKa plus log the conjugate base 1.1 over the acid. Okay, and then when you put that in the calculator here, okay, the Ka was negative log of 7.2, and the pKa, by the way, was 3.14 earlier, and then log of the 1.1 divided by 0.9 gives you 0.087, and we add that to 3.14, and that gives you a pH of roughly 3.22. So you can see, I consider that a very small change in the pH. We consider anything less than 1 to be a small change in the pH. Okay. Now let's say you added a strong acid such as HNO3. Okay. We can say we add, and I'm going to say we add the HNO3, so we'll say H3O+. Okay. So the H3O+, and I'll just this time we'll add let's do 0.05. Okay, this time the H3O+, an acid's going to react with the conjugate base, the F-, and okay, that becomes HF, okay, plus H2O. And before reaction, after reaction, you have 0.05 moles of this, 1 of this, and 1 of that. X out the water column, 0, 0.95, and 1.05. And then we're going to put this into Henderson-Hasselbalch. The pKa was 3.14 plus log, okay, the F- is 0.95 over 1.05. Okay, remember the pH equals the pKa, by the way, when the conjugate acid base pair is 1:1. Okay, we go 3.14 plus log 0.95 over 1.05, and that gives you a pH of 3.09. So you can see in this instance how the buffer can resist changes in the pH when you add a strong acid or a strong base to it. Okay, so hope that gives you a good solid background in buffers. Hopefully the understanding comes along soon enough, especially as we move into titration soon. Okay, that's it.